But sometimes, guess what? We have to have a multiplexer there because we bring it in some forwarded value that goes in, and then we have a control signal that triggers. Oh, instead of using A, use something that got forwarded to A. Now here I've only shown a 2-input mux. You know, it might be a multiple input mux. The point's simple though, right? It either picks, either the stuff that got fetched from the register is in A already, or it got produced somewhere else and we're forwarding it. All right? That's the idea. So we're now going to look at, okay, how it knows to do these forward paths as shown here. All right? And there are others. So here we go. So in this case, the source instructions in a register-to-register ALU that just entered the memory stage. All right, so here we go. So again, you can imagine what this looks like if you draw a pipeline diagram. For the sake of time, I won't. But all right, you can envision a register-to-register ALU instruction as the source. All right, and any of these is the destination. Okay, any of these is the destination. And notice for each, okay, blue, green, light yellow, or blue, green, yellow, orange, sky blue, and brown, I have examples that illustrate the case. So let's look at this top one, example 1. All right, it says it's a register-to-register ALU is the source. What's the destination? Okay, it's another register-to-register ALU, such as the end. There it is, right? And we know that it forwards, don't we? It goes from, where does it forward it from?
Execution to execution.
Right. The destination is where? The top ALU input. Where does it come from? I'm sorry, let's try this again. The source is where? XMY. XMY. And where does it go to? The top ALU. We sometimes, we might say that that's sort of the same as dx.a.
Okay.
That's the way we've been expressing it earlier.
Okay.
But I wanted to avoid that notation because it looks like we're putting it into a register. We're not really, okay? And here's the condition. You see it? Look. His destination register matches his first source register. Do you see it?
Yes.
All right. All right. There's another case that's very similar, which is example 4. Right? Example 4 is almost the same. Okay. Almost the same, except that he targets the bottom ALU when the destination is the same as the second source.
So that'd be like saying B, but not.
Yes, we used to say
B.
we used to say dx.b, but again, I want to avoid that notation because we're not actually putting it in the register.
So we need to
putting
start
it to the place where B would have normally gone through the use of these multiplexers.
So we need to start using top of ALU bottom.
You can use whatever notation. I'm not as concerned with specific syntax as I am with understanding.
Okay.
Right? Now that doesn't mean you're free to just make stuff up. And here are some other cases. So example 2, and you can go through these on your own.
Okay.
All right? You can go through these on your own to try to understand. And again, we could actually write the hardware that does this. Right? We can figure out what the hardware looks like. I say write hardware. How's hardware produced in modern times mostly?
AND gates and NAND gates.
Well, yes, but how do you produce the hardware?
Oh, from that fans.
You're using Verilog or VHDL.
Oh, you want the language?
Okay, so when I say you can write the hardware expression, I mean processor design. You don't have some dude looking at a schematic and the transistors out. Okay. You've got somebody with digital logic blocks gluing them together. Okay, in Verilog or VHDL or some other hardware description language. All right. So you could look at all of these and the corresponding examples to understand the logic that would be needed to cause forwarding to take place. And so the and of all of this, you know, this and this
equals
and this, right? If all of those are true, then instead of picking it from dx dot A, I would pick it from xm dot y.
Okay.
All right. Some more examples. This is a case of a register ALU that's just gone into the write stage. And once again, I've color-coded it, all right, and give you specific examples to illustrate the point, all right? So let's look at this one. So here I've got the source instruction is an ALU instruction, all right? And the destination instruction in this case is a branch. When does the branch need the data?
At the beginning of the code.
Decode, right? So even though it's 2 instructions down, right, I still need to forward it. All right? Hopefully you can see that. All right? So in order to implement instruction level parallelism using a pipeline, we have to know when to stall and we have to know when to forward. And those are the 2 families of logic that we're looking at here.
Dr. Morris, because we are parallel, because it is parallel, that is the reason why B and E is gonna stall from Daddy.
No. Well, yes, because you're trying to look. The dad instruction is getting ready to enter its write back stage.
Right.
At the same time, the branch instruction is getting ready to enter its decode stage.
Gotcha.
So in that sense, there's instruction overlap. By the way, there's 2 other instructions in between that I haven't shown. I've just shown them with dots. And assuming no dependencies there. So in the snippet that I've shown in example 6, there are at least 4 instructions being simultaneously executed, albeit in different stages.
Okay.
Right? All right. So you could go through these examples of the forwarding logic. Okay. Here's a case where the source instruction is an immediate that has just entered PM. There's really not much difference between this slide and, this slide. The difference here was an R ALU versus an immediate ALU. In both cases, it just entered M. They're virtually the same. Watch. In fact, just keep your eye on this one. Watch.
Okay.
All right. And there. Example 4. You see it's the same thing, X to X. You see X to X. Okay, the difference is here it was an AND.
And that's an and
here
intermediate.
It was an AND, assuming there's such a thing. And immediate. All right? All right, so forwarding logic. So again, even though we haven't drawn the specific AND gates or gates, it's not a stretch to be able to figure out, you know, in the XM's instance of the IR, all of the opcodes that translate into being an immediate ALU. I could build a piece of hardware, write a piece of hardware that does that. Okay. And again, so that's why I say that it's closer to being the logic. Okay, we're not actually down at the gate. So here's another one. This is an immediate that's just entered W. Very similar to the register-to-register ALU that entered W. Okay, so very similar kinds of logic. And then here's a load that just entered W. All right, a load that just entered W. Okay, and all the cases here. All right, and you can go through these. You know, so let's just pick one here. All right, so this is this light blue example, which is example 5. So here you've got a load. What's the problem? When's R7? When's the value that's in R7 available?
At the end of memory.
At the end of his memory stage, right? Two instructions later, when does the branch need it?
In the beginning.
Decode. So therefore you forward it. Bam. Do you see it?
Mm-hmm.
All right. All right. So, good. Now we want to talk about exceptions. All right? This is going to be a much higher level discussion, but it's worth talking about. So, an exception is associated with the normal execution orders changed. It's not the same as a branch where the flow of control is changed. This has to do with something happened. All right? Now, there's all kinds of words that are used. Exceptions, interrupts, faults, traps, aborts. A well-known example, divide by zero. Not defined, right? Not defined. So an ALU would have to know when that happened, and it would signal, an interrupt saying, hey, division by zero just happened. Maybe you want to do something.
So it's just like programming.
Well, yes. I mean, the reason you get these exceptions that you can handle in the program is because at the hardware level, there's logic that detects them.
Okay.
If it's a programmer-induced or a runtime-induced thing. So here are the various classifications. There's I/O requests, all right, operating system service calls, execution trace, breakpoint or interrupt, arithmetic faults, page faults. That's where the page that you need is not there in a virtual memory scenario. There's misalignment. I try to fetch a word from an address that's not a legal word address. A memory protection violation. My code tries to reference some segment of memory for which it can't, or it doesn't have the right read permissions, rather. An illegal instruction. There's some opcode in memory that doesn't mean anything. And then finally, there's some kind of hardware malfunction. So these are the exception types that we're looking at. By the way, I took this right out of one of the pages in the book. I thought I'd put the reference here. Apparently I did. It's not a big deal. I didn't make this up.
You just look for exceptions in the book.
Yes, it's in the book someplace. So now, within each of these classes of exceptions, there are a series of attributes. So things like, is it synchronous or asynchronous? Okay? Did the user specify it, or was it coerced? Was it forced on them? Can you turn it off or not? Okay? Some interrupts you can mask. Okay? Did it occur within an instruction, in the middle of instruction execution, or did it occur between instructions? All right? And then, what do? Do you resume or do you terminate? All right? So, let's take a look. Let's just pick one. An I/O request. Okay? When did the user press the keyboard? Okay, clearly asynchronous. Right? Who caused it? The keyboard. It's external. It's external, right? Right? I mean, you could argue, oh, it's user requested. By user, we're talking about the code that's running requested it. That's
okay.
not the case. Right? It's typically non-maskable. All right? It's typically between instructions. Obviously, after you handle that, you still have to resume, right? And you can look at the other ones. A page fault. That can happen, okay? That's synchronous, okay? All right? Because, it happened at a specific point in the execution of the code. It's a coerced exception. It's definitely non-maskable. You don't want to be able to say, ignore this. Okay, it happens right in the middle of an instruction, right?
Mm-hmm.
Doing my memory phase. Bam, sorry that page isn't there. Right? And you have to resume. Okay? There's some where you can just terminate illegal instructions or hardware fault.
A legal instruction like you typed the wrong letter or something?
Well, somehow the memory got corrupted. So I pull up an opcode that doesn't mean anything. Right? So, all right.
Dr. Morris, can it be grammatically correct but still not mean anything?
Now, remember, when we say illegal instruction, you're not talking assembly language code anymore.
Oh.
You're talking about the 30, in the case of MIPS, the 32 bits that are sitting in the instruction memory. That came first. A high-level language like C was compiled to produce an assembly language code. That assembly language code was assembled to produce the machine code that ultimately got loaded into the memory, right? So this is not English that we're talking about.
Okay.
This is, it pulls up the 32 bits and it doesn't know what it is.
Okay.
The hardware doesn't. And remember, we went through how the controller figures out what the instructions are. So if it's something that it doesn't know what it is, it just dies. All right? So, now, here's the deal with stop and restart. A restartable processor has to invisibly invoke the handler Okay, so some exception takes place. All right? Yeah, and the piece of code that deals with whatever happened is called a handler. So the keyboard handler. Okay, the illegal instruction handler. Okay, the numeric exception handler. Those are pieces of code, okay, that live somewhere in memory, okay, that do something reasonable to deal with the exception. All right, page fault. Bam, the handler is the operating system code that fetches the new page, puts it into a page frame. All right, so, good. So, invisibly, in other words, without external knowledge, it has to invoke the handler, which saves the executing program, then corrects or deals with the cause of the exception, restores the state of the program that caused the exception, and tries again. It has to do all of that, okay? Now, it turns out that there's this idea of what's called a precise interrupt. A precise interrupt, when you're using what's called a precise interrupt, then all the instructions before the faulting instruction are completed. In other words, everything to the right of that instruction in the pipeline. You empty the pipeline. All right? Flush. It's similar to a flush. It's similar to a flush. I don't want to use that terminology because, okay, it's similar to a flush. Everything before is completed. Then the instructions after are restarted from scratch. Okay? Now, it's usually implemented in integer pipelines because it's a whole lot easier than floating point pipelines. We'll see later that floating point pipelines can be really long. You know, we built a floating point adder and a floating point multiplier on an FPGA. Okay? The floating point adder was 14 clocks, and the floating point multiplier was 10 clocks. So very deep pipelines. Unlike integer add, which is single clock. To do floating point arithmetic, typically much longer pipelines. Okay? And precise interrupts support virtual memory. Okay? The problem is that they're difficult and quite slow for floating point pipelines. Now, some CPUs have what's called dual mode. So you put it in precise or slow mode to debug, and then after everything's running, you put it in the imprecise at runtime. Okay? Imprecise. All right? Very good. All right? So let's talk a little bit about, we're going to revisit data dependencies and hazards. All right? So, the context is almost always a pipeline processor, and these dependencies are critical to your ability to implement instruction level parallelism. Okay? Now, independent instructions can execute simultaneously or in any order without introducing hazards. If I get, okay.
Yeah, that's without depending on
right, anytime, all right? Now, dependent instructions, the ordering and timing is important, right? And if you do them in the incorrect order, or if you use the wrong timing, that can introduce hazards, all right? Now, there's two ways to deal with dependencies. The first is to keep the dependence but avoid stalls. What was the way that we did that?
By
Forwarding.
Sure.
By adding more hardware.
Right. Right? Yes, adding more hardware if it was a structural, hazard.
Rearranging the instructions.
Well, that was transforming the
Transforming.
code to eliminate the dependence. And again, the big weapon here is instruction rescheduling when you can do that.
Is that the same thing as renaming?
No. No, renaming we'll get to later.
Okay.
All right. Turns out that there are really three flavors of data dependencies. There's what's called a true data dependence, a name dependence, and a control dependence. And we'll look at each of these.
What? Flavors mean you.
Three different kinds, classes. After a while, your thesaurus fails. You start pulling.
I know you keep using
Flavor.
Flavor. I'm like, what?
Flavor.
You put pipe there.
You don't-
around my neck on a gold chain.
It can't work though. It can't work. It has to be broken.
I know. I've got in my car. Turn that off a minute. I don't want to waste the